99 panes of glass, 300 meters of open air beneath your feet. And the only thing standing between you and the canyon floor is a sheet of tempered glass 5 centimeters thick. Someone looked at one of the most dramatic gorges in China and decided to build a walkway made entirely of transparent floor. Welcome back to the channel. Today we are exploring what was at the time of its completion, one of the most audacious feats of pedestrian engineering ever attempted by human hands. This is the Zhangjiajie Grand Canyon Glass Bridge, a structure that redefined what a bridge is allowed to be. This is not just a walkway. It is a 430-meter suspension bridge built across a vertical chasm, engineered with a beam so impossibly slender that Chinese engineers described it as thin as a wing and as light as a swallow. And yet it must hold the weight of 800 people at once. This is not just a tourist attraction. It is a record-breaking monument to the idea that transparency itself can be structural. That glass, fragile, breakable, see-through glass can hold a crowd above a canyon. Imagine what the engineers faced: karst geology, riddled with faults and sinkholes directly beneath the anchor points. Winds screaming through the gorge at speeds that can exceed 200 kilometers per h, are a canyon so remote and difficult that standard heavy equipment could not even reach the site. A geological zone where the rock faces on both sides of the canyon were not uniform. They were cracked, ancient, unpredictable. The canyon itself drops 300 meters from rim to floor. That is roughly the height of an 85-story skyscraper. And someone decided we will build a glass floor here, a glass floor that people will walk across, and it will be the longest glass bridge in the world. Before we go any further, make sure you subscribe to the channel if you haven't already. We release deep dive engineering stories every week, and you do not want to miss what's coming. And stay with us until the end of this video, because what the engineers discovered about vibration, wind, and the physics of glass under human feet will genuinely change how you think about the ground beneath you. At first, there was only the canyon. No bridge, no cables, no towers, no glass. Just two cliff faces staring across 385 meters of empty air, carved out by millions of years of water cutting through karst limestone. The walls of the gorge were ancient and fractured. The canyon floor was invisible from the rim, hidden somewhere 300 meters below in shadows, moss, and the sound of running water. No road reached the site. No crane could be driven in. There was only rock, sky, and the void between. Here is the problem the engineers had to solve. If you want to build a bridge in this canyon, you need to anchor it to something. But the karst geology meant the rock was not solid. It was honeycombed with faults and cavities. If you anchor into weak rock, the whole bridge shifts. If the bridge shifts, the glass cracks. And if the glass cracks 300 meters above the canyon floor, you do not just have an engineering failure. You have a catastrophe. A conventional bridge would need massive steel beams 3 or 4 meters deep to carry a span of nearly 400 meters. But those beams would make the bridge a visual slab, a concrete wall across the sky, destroying the very natural beauty that made this site worth visiting. And if you tried to truck those enormous beams through Zhangjiajie National Forest Park on narrow mountain roads, you could access simply didn't exist. So the solution was not simple. It was not a conventional bridge, and it was not a conventional floor. It was an entirely new class of structure, a medium-span suspension bridge, with a girder so thin it had never been built at this scale before anywhere in China. Topped by a deck of triple-laminated glass, anchored into karst rock using precision, drilled deep foundations, and designed to be so visually light that it would, in the words of its architect, disappear into the clouds. The concept came first, years before a single bolt was placed. Israeli architect Professor Haim Dotan, founder of Haim Dotan, Limited Architects and Urban Designers, was commissioned to design the bridge. His vision was radical. The bridge should not impose itself on the landscape. It should surrender to it. It should be invisible. He envisioned a thin horizontal ribbon of white steel and transparent glass, suspended between the cliffs, so slender that from a distance it would look like a strand of silk floating between mountains. He called it his Bridge of Courageous Hearts. The structural engineering was handed to BRDI, the China Railway Major Bridge Rockanatis and Design Institute, the same organization behind some of China's most ambitious rail infrastructure. And construction on the ground began in 2014 with a team of engineers whose average age was just 28 years old. Then came the foundation work, and this is where everything began that would take 2 years to complete. The first task was geological survey. Not a survey you do from the surface, but deep drilling into both canyon walls to map every fault line, every cavity, every layer of rock that would need to carry the anchor loads. The engineering team drilled boreholes across the site, mapping the karst geology beneath each proposed tower location. What they found was not reassuring. Faults ran through the rock on both sides. Sinkholes existed nearby. The foundation zones had to be chosen with extreme precision, finding pockets of solid rock within the fractured karst, then engineering anchor systems that would lock into that rock without compromise. The supporting tower foundations were dug entirely by manual excavation. There were no machines that could reach the canyon ledges. Workers with hand tools cut into the rock layer by layer, casting foundation concrete in segments, allowing each section to cure before the next was poured. Every single cubic meter of concrete had to be mixed on site or carried in. Every rod of rebar, every bolt moved by hand through terrain that did not accommodate machines. Then came the 4 suspension towers. This was not simple. The towers had to be strong enough to carry the main cables and the entire bridge load, but they also had to be invisible. The engineering directive was clearer. The towers must look like they grew out of the cliff face. Each tower was clad in natural rock and covered with vegetation. Native plants and mosses that would grow across the steel and concrete structure until the towers appeared to be extensions of the canyon wall itself. Standing in the canyon below, you would not see man-made columns. You would see spires of rock, ancient, natural, and alive with green. The deception is total, and it took deliberate engineering to achieve. The towers were positioned 430 meters apart at the canyon rim, 430 meters between the anchor points, while the main span of the bridge itself would stretch 375 to 385 meters across the open void. Then came the cables. Every meter mattered. The main suspension cables were routed through the karst geology and anchored deep into the verified solid rock zones behind each tower. The cable geometry of this bridge was unlike anything built before at this scale. Rather than running the 2 main cables in parallel, the conventional approach, the engineers curved them inward, pulling the cable lines together at the center of the span. This created a V-shaped geometry when viewed from above, the 2 main cables converging toward the bridge's midpoint and the vertical wire suspenders fanning outward from those cables in a wide wing-like pattern. The result was a bridge deck that was 15 meters wide at each end, wide enough for visitors to spread out, narrowing to just 6 meters at the center. Not a uniform box, a shape that tapers like a lens or like the wings of a butterfly pressed open. The engineering reason was structure. The V-cable geometry distributed forces more efficiently across the span. The aesthetic reason was beauty. The bridge was meant to be seen from below, from the canyon floor and from above. And in every orientation, it had to look like it belonged to the sky. Then came the deck structure. And this is where the real miracle happened. The girder, the structural backbone of the bridge deck, needed to span 375 meters. At this length, a conventional girder would need to be 3 or 4 meters deep to resist the bending forces of a bridge carrying hundreds of people. The engineering team at BRDI took a different path. They designed a girder just 0.6 meters deep, 60 centimeters, for a 375-meter span. That is a span to depth ratio of 625, a number that breaks the records of Chinese bridge engineering. It had never been done before at this scale in China. The chief engineer on the project described its simper as thin as a wing, as light as a swallow, a light slice floating in the sky. The girder was constructed from 2 parallel steel longitudinal beams running the length of the bridge, connected by transverse cross beams at regular intervals. The whole structural frame was assembled piece by piece, each segment carried to the site manually or by small equipment across the canyon rim. then lifted and connected across the open void because no heavy cranes could operate at the canyon edge. The bridge components were designed to be modular and lightweight enough to be positioned by smaller lifting systems working from the rim. Then came the glass, and every single pane mattered. This was not window glass. This was not any glass that had existed in this application before. Each of the 99 floor panels in the bridge deck is a 3-layer laminated system, 3 sheets of tempered glass bonded together with structural interlayer material, forming a composite slab approximately 5 centimeters thick. Each panel measures 4.42 meters long and 3.01 meters wide. Each panel weighs approximately 1.5 tons. The engineering requirement was extreme. The glass had to be transparent, completely, fully transparent, with no frosting, no tinting, no obscuring of the view below, while simultaneously being capable of supporting the live load of multiple people walking, stopping, pressing down, shifting their weight, crowding together. It had to resist thermal expansion in summer heat and contraction in winter cold without cracking. It had to shed rainwater without becoming slippery. It had to be testable, verifiably safe before a single tourist stepped onto it. The 3-layer lamination was the answer. If the outermost layer is ever cracked by impact or stress, the middle and inner layers remain intact. The structural bond between layers means even a cracked outer pane continues to carry load. The panels were designed so that any single pane could fail without the bridge deck failing. This was the non-negotiable requirement, redundancy, because the alternative was unthinkable. In total, the glass components, the steel frame, the cables, the towers, the complete structure weighs approximately 2,200 tons. Without cables, 2,200 tons of engineered metal and glass hanging across a 300-meter void. Then came the wind testing, because no one had tested a glass-decked bridge of this length in this wind environment before the engineers knew the canyon was a wind tunnel. Storms pour through the Zhangjiajie gorge with tremendous force, channeled and accelerated by the narrow walls. The bridge simulation was sent to the wind testing laboratory at Hunan University for 6 months. Scale models of the bridge were subjected to wind velocities reaching 56 meters per second, approximately 201 kilometers per h-hour arrow. Elastic tests, flutter analysis, dynamic simulations, gravitational stiffness under simultaneous wind and crowd load. What the tests revealed required careful engineering response. A long, slender glass-deck suspension bridge can be excited into resonant vibration, the same phenomenon that destroyed the Tacoma Narrows Bridge in 1940. The engineering team designed specific countermeasures into the struck dampers, shock absorbers, anti-vibration mechanisms embedded throughout the bridge frame. They also installed approximately 50 glass spheres weighing 500 kilograms each, precision counterweights that act as tuned mass dampers, absorbing energy from oscillations before those oscillations can build into dangerous resonance. Beneath the bridge beams, 2 large water reservoirs were added as additional damping mass. The original design also called for glass guardrails along the sides of the walkway. Wind testing killed that plan. The gusts through the canyon were too strong. The glass handrails would have acted as sails, transmitting massive lateral forces into the deck. Steel pole handrails replaced them. Every decision was made in response to reality, not theory. Then came the test loading. And what they did here was remarkable. Before the bridge opened to the public, the engineering team had to prove that the glass floor could survive not just the design load, but extreme abuse. They brought in bulldozers and drove them across the glass. The glass held. They tested it with concentrated point loads, with distributed crowd weights, with dynamic impact simulations. They tested every single panel's integrity individually before installation. And then they tested the installed panels again. The procedure was certify the glass in the factory, install the glass on the bridge, test again in place, because the environment of the canyon, the temperature swings, the humidity, the wind-driven vibration could affect glass behavior differently than a factory floor. The bridge was completed in June 2016. After final inspections and safety certifications, it opened to the public on the 20th of August 2016. In its first days, the crowds were enormous. Daily visitor numbers were capped at 8,000 people, nearly 10 visitors per minute across the operating day. The bridge had to be temporarily closed shortly after opening because demand overwhelmed the system. Not because of engineering failure, but because word had traveled across China faster than the ticketing infrastructure could handle. When it reopened, it did so with a permanent daily limit of 8,000 and a maximum of 800 visitors on the deck at any one time. Most visitors who walk this bridge see the view. They see the canyon unfolding beneath their feet, the forested walls, the thin ribbon of river 300 meters below, the waterfalls threading down the rock faces, the clouds level with their shoulders. They see the extraordinary fact of standing on transparent glass in open air. They do not see the 6 months of wind tunnel testing that proved this bridge would not oscillate itself apart in a storm. They do not see the geological borehole data, the drill cores pulled from the canyon walls, mapped and analyzed, that identified the exact pockets of solid rock where the anchor systems could be trusted with thousands of tons of load. They do not see the 50 glass spheres embedded in the structure, each one swinging with microscopic precision to cancel the resonant frequencies that would otherwise build in the deck. They do not see the water reservoirs hanging beneath the beams, silent, heavy, absorbing the energy of the wind. They do not see the 3-layer lamination in the glass beneath their feet, the invisible redundancy that means even a cracked pane keeps bearing load. They do not see the 28-year-old engineers who stood at the edge of this canyon in 2014, looked across 385 meters of open air and ancient karst rock. That is the real story of this bridge. Not the view, the decision. The decision to design a 2,200-ton structure thin enough to look like it was there. The decision to put transparency where other engineers would have put mass. The decision to let the canyon win, to let the landscape be the architecture. Without the precision anchors, the bridge falls. With them, it floats. Without the dampers, the wind owns the deck. With them, the deck owns the wind. Without 99 panels of triple-laminated glass, tested to failure and back, 1 million visitors have nowhere to walk above the clouds. With them, they do. Haim Dotan wrote a poem about this bridge. He called it a dream in nature, a dream for music in the clouds. He was right, but behind every dream is 2 years of construction in a karst canyon with no road access. 6 months of wind tunnel testing in Changsha, a team of engineers whose average age was 28, and the simple, extraordinary commitment to get the glass right. If you enjoyed this video, subscribe to the channel and leave a comment below, telling us, would you walk across it? Thank you for watching.